channel. I'm Spira. I'm an optical engineer. I am a technical enthusiast. I am a music producer. I love to build Arduinos for audio production modules, and I love optical microscopy. So in today's video, I'm going to show you how to build your own confocal microscope. So if this is something that interests you, if you're a technical enthusiast, music, light, optics, please subscribe to my channel and I will continue to share more. So today I'm going to show you how to build your own confocal microscope. Now, this is not necessarily a hobbyist project. This is more geared towards somebody who has access to an optical laboratory and also someone who has advanced laser safety training. This is very important. Disclaimer, protect your eyes and vision. But in this video, I'll show you from start to finish how to build a confocal microscope. I will overview the basics of confocal microscopy, tracing the optical path with mirrors and lenses. I will explain the source light and the detection and how to render that into a constructed image. And I will go through the basics of optical alignment and show you some of the tools that you will use in an optical laboratory. The mission is to empower you to use light and to use sound and to use electronics to harness your creativity and your creative energy and go use it to build something really cool in the world. So come with me into my laboratory, let's go! Now, before we're able to step into the laboratory, I need to give an overview of confocal microscopy. So confocal microscopy provides high-resolution imaging to resolve detailed cellular structure at an exact plane of focus. Confocal microscopy achieves this through utilizing a small pinhole or aperture to focus the light and reject all out-of-focus light. So this improves resolution. Then this small focus point is scanned across the object, and each point is reconstituted into the image. So this requires a confocal pinhole and a scanning mirror. And each point that is scanned will be reconstructed to create the entire image. So an optical system essentially collects and reshapes an incident wavefront to form an image. So light is projected from a source to an object, and then from that object to an optical detector. So we need a source, which in this case is a laser. We need a detector, which in this case we used a photomultiplier tube. And then the optics in between, like lenses and mirrors, they shape the light to focus on the plane. So confocal microscopy utilizes a combination of a 4F imaging system and a 2F imaging system for scanning. The 4F imaging system is the typical imaging system in, say, a wide field microscope, and this consists of two positive lenses with the object or the sample plane one focal length in front of the first lens, the objective lens, and the detector located one focal length after the second lens or the tube lens. So in a 4F imaging system, the output is an inverted replica of the input, where the magnification is dependent on the ratio of these two focal lengths. So these Fs for the 4F or the 2F imaging system, they just refer to the focal length of the lenses, and this becomes important in the geometric optics of how far apart we're placing these lenses. They're going to correspond to the focal length. So now getting into the confocal element of this, between the two lenses, the scanning lens and the tube lens, lies the Fourier plane, which corresponds to the spatial frequency, and the second lens reconstructs the image. So an additional 2F system relays the scanning MEMS mirror placed a focal length from the scan lens to input of the 4F system, where the scan angle can be measured as the displacement on the conjugate plane. So this is a product of the maximum mechanical angle of the MEMS scanning mirror, and the lateral displacement at the sample plane is then demagnified by the 4F system. Notice at the input at the scanning mirror, this light is collimated, that means it is going straight. So that is our first focus, is to collimate a laser through the system, and then we will manipulate these magnifications by adding lenses in our system. We want collimated light between our tube lens and our objective lens. So let's show how we achieve this. A quick reminder about the nature of light. We treat this as both a photon and as a waveform. So the ability to resolve the spatial frequency at the Fourier plane are related to the wave-like nature of light. We also have to address aberrations in our system. So looking at our optical design on our breadboard, the breadboard is used to stabilize any vibrations that might disrupt the system. Starting at the bottom right, we see the Sapphire Coherent 488. That is our laser. That's 488 nanometers. That is put through two mirrors, which help to fiber couple our light. So we need this light to be collimated into our system. We would like to fiber couple it. That means we're running this through a fiber. And to do this, we use the tilt and turn knob on two mirrors to get this light to perfectly direct into the objective, which can be translated through a fiber. And this light can move all the way through the fiber and out into the fiber collimator. So now this light is collimated. This is moving straight. It's not focusing. It's not diverging. And now there's two mirrors, M3 and M4. We use the tilt and turn of these two mirrors to focus into the MEM scanning mirror. Now this is our scanning mirror for our system. Once it is focused into the scanning mirror, it moves through the scan lens SL and then through some filters. There's an emission filter, an excitation, and a dichroic filter. This helps to filter the light that is incident on the object. We would like to detect a very specific wavelength, and this dichroic filter actually will help us to filter the returning light into the photomultiplying tube. But for now, we are going straight through the dichroic to the bottom. Ignore the removable folding mirror for now. That is another system, so we coupled this system to a wide field microscope as well. This mirror is removed right now, and it goes straight through the tube lens into a fifth mirror and into the objective, which is then fiber coupled to the FCM. That's our fiber coupled microscope. Now in this case, the fiber actually acts as our confocal pinhole, so we don't need an aperture here. And then once the sample is collected from the fiber, the light is redirected back through the system. Now it passes through M5, mirror 5, through the tube lens. Now it goes to the dichroic mirror, and now it is spectrally shifted, so it cannot pass through the dichroic mirror. Instead, it is reflected. It is no longer a filter, it is a mirror. This is reflected and filtered through the bandpass emission filter into the photomultiplying tube. The photomultiplying tube is where we will collect our signal. Now, for the other module, we also have a wide field microscope. This helps for easy focusing without needing to run our laser. The wide field microscope in this system has LED light. We again use an excitation filter to bandwidth the light. This passes through the dichroic into the tube lens, the objective, through the FCM, and the light passes back all the way to the dichroic. And now this dichroic acts as a mirror. It can no longer pass through the dichroic, so the light is directed into the emission filter and into a camera. And this is a 4F imaging system with outer confocal. So for the purposes of this video, I actually skipped through the laser alignment for our collimating lens, but know that we took the output from the laser and aligned it in these two mirrors to be directly input into an objective, and that was fiber coupled and then spit out into our breadboard in collimated light. Now in this image, I show you the main microscope setup, and this is our confocal setup. This is just the physical setup for what I explained in the light path. And then I also share our wide field module with the camera. So now that I've given you a general overview, stick around for part 2, where we will actually get in the lab to start aligning some optics.